Talk about linear versus angular speed. Now, this is related to the picture that I have over here. We sort of naturally understand that if we have runners in a race, this is actually a picture from the Paralympics. If we have runners in a race and maybe they're only running one lap, that we need to think about staggering their starts because depending on where they are in this track, it's not exactly a circle, but you can kind of think about it as circular kind of parts to it or circular like parts to it. That's more of an oval. But where we end up starting these athletes depends on how far they are away from the center. The ones in the innermost are going to have the shortest part if they just ran exactly back to the start, whereas the guys out here are not going to have to go as far, meaning they should start further up so that when they reach the finish line, each of those distances represents the same distance run. In other words, if we all started them kind of back here on this line and they ran a complete lap, the guys on the end would actually be running farther than the people here. So we kind of understand this intuitively, and we're going to connect this idea of arc length and how that affects things to linear and angular speed. So related to this, we can think about what would happen if they run at the same speed. They would kind of form different angles as they run, but we could also contrast this and think about the same angle and contrast the linear speed. So that's a little bit abstract. I'm going to show you guys an illustration. So I'm going to start, and I want you guys to notice that the angle that's being swept out is the same. I'll play this again in just a second. The angle that's being swept out is the same. In other words, they're maintaining the same angle, but I want you guys to look at the motion. Now you can tell just from watching this one that the orange dot seems to be moving faster. If they both make two complete circles, in this case, two complete circles in this, it's actually a 10-second increment, that the orange runner has to be running further because he's running around a bigger circle. So this sort of idea is going to help us understand the difference between angular speed and linear speed. We'll play it one more time. But in this particular picture, the angular speed is the same, but the linear speeds are different. So what we want to do is make sure we understand how to compute angular speed and some of the difficulties there, and then also how to find linear speed if you know an angular speed. So let's go ahead and think about what angular speed is. Sometimes we'll use the symbol omega. You'll see that some for linear, or excuse me, for angular speed. Sometimes we'll use the symbol omega for angular speed. You may see that if you take a physics class. But angular speed is how many radians you move through. So think about this as the change in the angle, typically in radians, over the change in time. So how many angles or how many radians you move through, I should say, the angle you move through over the time period. So let's make this a little bit more concrete by just kind of giving a specific example. So let's say we make 2 revolutions per minute. Sometimes we'll see this or revolutions per minute, just abbreviated. And in fact, we're kind of used to seeing RPMs maybe on our car. You could also have revolutions per second, revolutions per hour if we have something that's kind of more slow moving. But revolutions per minute tells you how many times you're revolving in a particular minute. Now, in this particular scenario, revolutions are related to angles, but they're not angles themselves. So I want you to think about 2 revolutions. Well, that's actually 2 pi angles. In other words, 1 revolution is 2 pi radians. So 2 revolutions is really 4 pi radians. So if you had something like 2 revolutions per minute, the angular speed, you could call it omega, but your angular speed is 4 pi radians per 1 minute. Now I'm kind of writing it like that so that you see this per minute allows us to think about per minute here. So you have 4 pi radians per minute. Now, Sometimes you might have your answer like that, or it's possible you could also have your answer in a decimal depending on the form. If they just say find the angular speed and they don't say convert to decimal, maybe leave it with a pi. But let's go ahead and find the decimal representation. So if we go ahead and just convert that 4 pi to a decimal, then this is actually telling us that this is approximately 12 point, we'll call it 57 radians per minute. Now, if you are asked to do any sort of time conversion, like they change from minutes to seconds or something like that, you have to work a little bit harder. But in this case, we just wanted our angle measurement. You can kind of look at the units they have for us. We're just going to leave it as radians per minute. If they wanted something like radians per second, for example, then you could go ahead and convert those minutes to seconds and do a little bit more. All right, so let's take a look at uh, now linear speed. So when we talk about linear speed is the idea of the distance over the time. So when we're talking about just like motion in a straight line, then we can do distance over time. Now, just kind of go back to the circle for a second. I want you to watch one more time. And when we're in motion in a circle, we can actually kind of simplify this and make it a little bit easier to talk about. You can see that you're going faster. The linear speed, like the running speed, is faster than the orange than it is in the purple. So in a circle, what happens is the linear speed is bigger for a bigger radius. So what happens is you multiply the angular speed by the radius. So I'll abbreviate just a little bit. But one way to do this, sometimes you'll see linear speed is like V for velocity equals R times your angular speed. Now, keep in mind, you have to still, if you have something in revolutions per minute, convert here, but then you would go ahead and use that angular speed. This has to be in radians per some sort of time. So on the bottom, you might have something like minutes or seconds, some sort of time unit, but you need to make sure it's in radians. You don't want degrees and you don't want revolutions. So let's take a look at a specific example. We'll move this. And let's go ahead and give an example. We're going to think about maybe a bike wheel. So let's say we have a bike wheel, and let's say the diameter of that bike wheel is 18 inches. And let's say that the tire is rotating at 4 revolutions per second. So if we have the bike wheel and we're given this, I forgot to write this here, but I said a diameter of 18 inches. So that's usually how they give a bike wheel. And then we have revolutions per second. You want to be really careful that you make sure that if they give you a diameter, you think about the radius. You scale out the angular speed by multiplying by the radius instead of the diameter. And then you want to make sure that you're also converting this to an angular speed that's in radians. So think about the quick way to do it is if they tell you the revolutions, multiply by your 2 pi. So this is actually 8 pi revolutions, or sorry, radians. Sorry, guys, radians per second. And then let's go ahead and just put, I'm going to put Desmos back up here. So if we did 8 pi, sometimes when I'm writing and saying, it's a little tricky, but 25.1, we'll say 1.3 approximately radians per second. Okay, so this is the angular speed. Now, let's say we want to know the linear speed. The linear speed you can kind of think about as if you had a rock stuck in the bike tire. How fast would that rock be traveling around? It turns out that how fast the rock travels around the outside the circle is actually the speed that you're moving if you were to take that bike This is a bad drawing. But you take that bike and you move it in a straight line. In other words, the linear speed is actually the speed of the bike, or you could think about something traveling around the outside of the tire. Because as you move around the outside of the tire, you're moving the bike forward that distance as well. So if we wanted to know the linear speed, we'll change colors here. The linear speed, we're going to take that radius. So this is 9 inches. And I'm going to leave off the inches for a second, but I'm just going to write it kind of on top because I don't want us to miss the units here. And then I'm going to go ahead and multiply by this 25.13. Sometimes if you are putting in that 25.13, I'm going to show you guys just kind of a little bit of round off error here. You want to be a little bit careful, but this is radians per second. We don't actually have to write the radians, so you can kind of think about those dropping out. So this is going to be inches per second. So just to kind of show you guys some of the things that can go wrong, if I just put 25.13, about 226.26. Oh, sorry, guys, I typed a 4 there. 226.17. Now, just kind of contrast that. I'm going to move this up a little bit so we can see here. If you go ahead and just put 9, and then you put in that exact 8 pi, instead of the decimal representation, notice that to 2 decimal places, you're a little bit different. This is just kind of round off error. So you can either go back to the unrounded version, or one thing that I'll often do is like a copy and paste here. So if you, sorry guys, if you copy the unrounded version and then just drop that in, I just want to show you guys, and that's going to give you the right part. So what I don't want you to do is I don't want you to miss homework questions because you're just off based on the rounding. You can see that that accumulated error can cause some rounding issues. So you want to either copy and paste with that unrounded answer, or you want to go ahead and use the exact. So here, use unrounded, or you could do 9 times 8 pi. So in the end, our linear speed in this case is we are 226. I'm going to go 2.19. And then our units for this are going to be inches per second. Okay. So let's talk about how fast 226 inches per second actually is. So if we did a quick Google search, we could just kind of ask Google how fast this is, or like a conversion. It's kind of underneath there, but you can see we're about 12.8 miles per hour. In other words, this might be a biker kind of moving at a moderate pace. So a lot of times when you're working an applied problem, you might not have to rescale your units. So you might just be here and done. Other times you might have to maybe convert this to feet per second, or maybe you would want to go from a feet per second to an inch per second scenario. All right, so if you don't have to convert, you're finished, but let's just kind of illustrate that conversion really quickly. So if on this one, you're trying to do that conversion and you want to take your 226.19 inches per second, keep in mind when I actually put this into decimals, I'm going to copy and paste the unrounded version so I don't use or lose decimal accuracy. But think about that as that's how many inches per 1 second. Let's say I wanted to convert this to feet per second. So if I wanted to convert to feet per second, I would want to get rid of the inches and come out with feet. In other words, cancel those. So we know that in 1 foot, there is 12 inches. So we're going to have fewer feet per second than we do inches per second. So you could also think about if you had to go the opposite direction, you could multiply by 12, going from feet per second to inches per second. But let's go ahead and take a look at putting this into decimals. All right, so I'm going to get rid of just a little bit of this stuff just so we can kind of see what's happening here. Okay. Sorry, guys, that's taking a little bit of time there. My eraser is super small. Thank you for your patience there. But what we want to do is go ahead and multiply. So I'm just going to do my copy and paste there. And then I'm going to multiply by 1 over 12 or divide by 12. And this is going to be approximately, if I round now from this one, 18.85. So again, don't put it in like this, put it in like this. And this is going to be, sorry guys, feet per second. All right, that's it for this video. Just be really careful that you have your angular speed in radians per time unit, and then be careful with your unit conversions.